Hi, everyone. So before I show the demonstrator, I'll just give a brief summary of the project. So I was the lead researcher on the project. So if you have any questions about the demonstrator or about the project in general, then feel free to contact me. There's my address there. There was also some company partners on the project who gave some input, which was very helpful. So yeah, just to briefly give the motivation of the project. It's obviously in the interest of both households and businesses to reduce their power consumption as much as possible. So this saves money and it also reduces emissions, which is very important. So one way to reduce your power consumption is to optimize your power systems. So this could be the heating and cooling systems on a household level. If you're thinking about industry, it could be some kind of manufacturing systems. You want to optimize these to reduce their power consumption as much as possible. And there's many traditional methods to do this, but they run into some problems for very complex systems. So there can often be difficult to design solutions for these very complex systems. So this is where reinforcement learning comes in. So reinforcement learning is a kind of machine learning that learns using trial and error. And thanks to some high profile theoretical and practical successes recently, it's been well established that it's very well suited for control problems. So to showcase the potential for reinforcement learning in power optimization, we decided to focus a demonstrator on the problem of optimizing building heating and cooling systems, which are often called HVAC systems, which stands for heating, ventilation, and air conditioning. So the demonstrator, it provides a really simple building heating and cooling simulation, and it allows you to compare reinforcement learning methods with rules-based methods. So I will just switch to the demonstrator now. Okay, here it is. So this is the homepage of the demonstrator. In this introduction section, we outline the general setup for the simulation. So pretty much the simulation is a small building with heating and cooling systems. And throughout the course of the simulation, the building is subject to changes in outdoor temperature. And these changes in outdoor temperature means the building either loses or gains heat to its surroundings, depending on the temperature difference. So the goal is to operate the heating and cooling systems in the building in order to maintain indoor temperature. In this case, we've chosen to maintain it between 23 and 25 degrees. So that 2-degree window is what you're going for. So the simulations last for 7 days, and they use real-world weather data for the outdoor temperatures. So in this case, the weather data is from Canada, which was chosen because there's quite a lot of extremes in Canadian weather. It gets quite hot during the summer and gets very cold during the winter, which allows for very robust testing. So if you go down, you'll see the simulation configuration panel here, which gives you several options for the simulation run. So you can choose whether to run it in winter, which would be a focus on heating, or run it in summer, which would have more cooling involved in it. You can choose whether to run it with one room with a single HVAC system, or 2 rooms with 2 HVAC systems. And there's these 2 options here, scheduling and dynamic pricing, which I'll explain shortly. So if you run the simulation, it takes about 30 seconds to run. So I'll just show you one I made earlier here. So this is a simple 1-room simulation for winter weather. The first thing you see on the results page is this table here, which gives you some metrics for performance. So the first column here, power consumption, is quite self-explanatory. It's just the overall amount of power used by the heating and cooling systems throughout the course of the simulation. So obviously you're trying to minimize this as much as possible. So in this case, the reinforcement learning method has slightly outperformed the rules-based method. There's also this column here, number of actions per hour. So in a real world scenario, you want to minimize the amount of toggling of the HVAC systems, so if you're constantly turning the heating on and off or constantly turning air conditioning on and off, that's going to wear down the systems, and it'll increase your maintenance costs as well. So we're trying to minimize number of actions. In this case, again, the reinforcement learning model has outperformed the rules-based system. This other column here, time spent out of comfort zone. So this is the proportion of time in the simulation where the indoor temperature is outside of that window we set between 23 and 25 degrees. So again, you're trying to minimize the amount of discomfort here. So reinforcement learning has again outperformed the rules-based one. This last column here is the average size of the temperature deviation. So when you do deviate from that window of comfortable temperatures, how much do you deviate by on average? So in this case, the rules-based system is the one which is slightly better in this case, an average deviation of 0.3 degrees. So below that table, you have plots of temperature here. You can compare the indoor temperature to the outdoor temperature for the course of the 7-day simulation. And you can see here, there's a lot more, there's much more fluctuation for the rules-based system, which you would kind of expect looking at the number of actions per hour. On average, there's a lot more changes in the heating and cooling state for the rules-based method, which leads to more fluctuations. Below that, there's a plot of the heating and cooling levels. So there's 2 different heating levels you can have. The second one is slightly more powerful, and there's one cooling mode you can have for the heating and cooling systems. So again, this just shows you that there's been much more toggling for the rules-based system here, which you would expect again from the table above. And you'll notice that there's also been no cooling used in this simulation, which is to be expected because it's winter weather there. That blue line, it's very low temperatures. There's no need for cooling really. So yeah, I mentioned this other parameter you can add called scheduling. So this is where the temperature goals drop by 5 degrees during the night. So during the day, you're trying to keep the indoor temperature between 23 and 25 degrees. During the night, you're trying to keep it between 18 and 20 degrees. And this kind of, it increases the complexity of the simulation and kind of roughly models real world behavior. So in general, people don't leave their heating on all night, or they'll like try and keep a lower temperature during the night. So we can see the effect of this scheduling here in this simulation run I've made. So here, if you look at the indoor temperature, you see it fluctuates between 23 and 25 during the day, and then decreases down to between 18 and 20 during the night, which is what we want in this case. And if you look at the metrics here, the reinforcement learning model has really significantly outperformed the rules-based method, which is kind of what we'd expect because it is especially suited to complex scenarios. And this introduction of the scheduling, it makes things a bit more complex and difficult. So yeah, it's outperformed on all metrics here compared to the rules-based system. Another thing we can do, as I mentioned earlier, so you can have a simple simulation with just one room and a single HVAC system, where you can have a more complex simulation with 2 rooms. So these 2 rooms have different thermal properties. So you could imagine, one is bigger than the other, one has more windows than the other, or something like that. And each of these rooms have their own independent HVAC systems. So if we look at one of the simulation runs here for the 2-room scenario, you'll see there's significantly more power used, which is to be expected because it's a bigger building. It's going to cost more to heat it. And if you go down and look at the heating and cooling level plots, you'll notice that there's 2 lines in this case. One for the heating and cooling state of the first room, one for the second room. And you'll see these lines diverge, showing that there's different behavior for each room, which again you would expect if they have different thermal properties. There's going to be divergence there. Um, so yeah, that sums up the basic working of the demonstrator. There's a lot more combinations you can have between all these different parameters. But yeah, that shows you the basic workings of it. Yeah. Um, yeah, and again, if you'd like to contact me or anything, just email me at michael.spence@ucd.ie. Thanks very much for listening. Thanks.